Good morning, panel. I, Mr. Lafradez, together with my groupmates, Mr. Meala and Mr. Olivarez, are the ones who created Bagwis. But before we tell you more about Bagwis, do you know that as the country moves forward in terms of smart agriculture, it is encouraged that as young engineers, we contribute towards this innovation. Thus, the idea of Bagwis started. Problems encountered in this study were the calibration of the drone for stability in its flight, the ability of the system to properly identify parameters needed in the study, and the creation of a user interface which will hold the data gathered securely as we are in the era where cybersecurity is a necessity. This study was done to be an effective aid in crop production and the necessary quality control. As we are an agricultural country, a big part of our economy relies on the agricultural produce. Keeping in mind that our target market will be the agriculture-related companies, we made sure that our system will be cost-effective.
Our system was composed of three main objectives that primarily focuses on flight, camera, and user interface. So based on what is written, the flight objective was to develop a flight pattern of the UAV for the remote sensing that is equipped with a cost-efficient RGB NIR multispectral camera capable for greenhouse use. The pandemic drastically changed the view of this objective, for we are constrained in our homes. In result, the pandemic did not allow us to physically deploy our aerial vehicle in the required environment. But the UAV's configuration was still designed for the controlled environment. Next is camera. Our goal was to design a camera system and image processing algorithm for the purpose of identifying the vitality of vegetation. But similarly, the pandemic did not allow us for the collection of the data through the camera within the specified environment. Therefore, an alternative approach was completed. Vitality basically includes crops' overall health in terms of NDVI, the crop's chlorophyll content in terms of CVI, and the crop's water stress in terms of PRI. This objective primarily focuses on the multispectral camera or imaging of the system. Lastly, the user interface. It basically states to create a user interface that enables data transfer and display of gathered information of the overall system. So basically, this would be the output part of our system.
For the scope, we have visual, RGB, NIR, and capture standby hover. First is visual. Since the main sensor for our input is a multispectral camera, the system would solely depend on the physiological parameters, which generally includes the structural information of a crop, primarily its color. Multispectral camera system only focuses on green leafy vegetables, more primarily the lettuce. So for the RGB NIR, the camera system can only manage information from the visible and near infrared wavelengths or frequencies, which focuses on the crop's quality. Similarly, there are only three parameters included, which are NDVI, CVI, and PRI. If the future researchers wanted to increase the capability of this detection, therefore the range of frequencies should be increased. Lastly, capture, standby, and hover. The flight of the system is limited to the flight pattern uploaded within the flight controller's memory system. Therefore, it can only follow a path or waypoint that is indicated in the given flight plan. Flights can basically be varied if the user would re-upload another flight plan. This limitation only occurs for autonomous mode. Limitations. First, we have input image. Second, we have implementation. Images were taken from the internet instead of them being acquired. These images are basically vegetables or lettuce which have clear green appearance. So for the implementation, the alternative approach prohibited the drone to be used in an actual greenhouse farm. But still, we managed to design the drone at a certain configuration that it can be operated in a controlled environment. One of the literatures regarding the aerial vehicle was entitled Capabilities of Flight Controllers for UAV Flight. This primarily focuses on building an unmanned aerial vehicle with the currently available flight controllers. So basically, there are flight controllers which are cube type and there are flight controllers which are microchip type. It can be concluded in the paper that the cube type flight controller is easier to configure than a microchip type controller. This microchip type flight controller is a device that required heavy coding which would generally take a lot of time in building the whole system. The cube type is an all-in-one flight controller, where you can only plug and play the various components of a given aerial vehicle. This type of flight controller requires only the available ground control station in order to configure the UAV itself.
The paper entitled Low-Cost Multispectral Imaging for Remote Sensing of Lettuce Halt demonstrates a low-altitude UAV-based remote sensing of lettuce where capturing of images was done with the use of digital camera. For many green vegetables, a decrease of plant health leads to reduced intensity in the NIR range of the spectrum and increase in the visible region. A typical reflectance spectra for healthy and less healthy lettuce are shown in the figure. It can be seen that the visible reflectance changes little between health status, but the NIR reflectance changes markedly. One of the most widely used vegetation indices, the NDVI, has its numerator NIR-red. Therefore, the NDVI would be large for healthy lettuce but small for unhealthy lettuce, making it a particularly sensitive indicator of plant health. Another paper showcasing the second index used for image processing was defined by the journal entitled the Photochemical Reflectance Index as a water stress index. The PRI is another commonly used and analyzed index for crop water stress assessment. This is related to the changes in the total carotenoid of the plant. The PRI was correlated with measurements of photosynthesis where there is an increasing intensity of photosynthetically active radiation or PAR. The said radiation measures the amount of light needed for photosynthesis, which is around 400 to 700 nanometers in the spectrum. As shown in the graph, increasing PAR reduced the value of PRI for both water stress and controlled plants. This means that PRI is increasing if the plant was experiencing water drought. Here is an overview of the system. The first one will be mission planning. This is a full-featured ground station software that was used in configuring the UAV. Second, image acquisition or input image. The raw images of RGB and NIR were uploaded to the created program for vegetation analysis. Third, image processing. Generally, this will be the heart of the system. In terms of obtaining the vegetation indices of the raw images, it aims to improve the quality of image needed for determining the plant's parameters. Fourth, data compilation. This serves as compilation of the computed values gathered from the process. Lastly, user interface. The user interface showcases the homepage, dashboard, and inputs of images for processing.
For the hardware of their aerial vehicle, these are the components. So we basically have the flight controller, switch, the GPS, the buzzer, telemetry, PPM receiver, the power module, power distribution board, ESC, motors, a battery, and for the camera system, we have the RGB camera, NIR camera, the microprocessor, and we have a power source. So basically, the main component of this system is the flight controller, which serves as the brain of our system where all devices are connected. This controller controls other UAV components with the user commands. Next is we have firmware. So in the firmware, we have three main components. We have the drone itself, MavLink, and the ground control station. There are two applications present within the UAV system. One is the ground control station and the controller firmware. We first install the ground control station, for it is also the platform where you can install or upload the firmware for the flight controller itself. This was the most important part of making the vehicle, for every type of aerial system has its own firmware. In our case, we use the quadcopter firmware. This would generate the basic configurations for setting up the quadcopter. Once this is all done, the components of the aerial vehicle is calibrated, ESCs, manual controllers, the telemetry are all calibrated within the ground control station. This MavLink is a message protocol which allows communication between the drone and the ground control station. Since we are using a cube-type flight controller, connecting the telemetry of both the vehicle and the control station through MavLink was done easily through the ground control application itself. Next is we have flight. In the ideal scenario, it starts by arming the aerial vehicle. Once this is done, the drone would take off in order to access the waypoints indicated within the flight plan. There is a given delay whenever the UAV reaches a certain waypoint, in order for the user to manually trigger the camera with an external button. Once navigation is done, the UAV will return to its launching position. This concept occurs in autonomous mode. This is a picture of the manual mode, where each button or stick is basically configured in terms of its climbing up, spin, right, forward, and more.
Here is an overview on how the image processing works. The proposed method on how the image can be gathered before the pandemic had occurred was by camera. With a camera, the respective RGB and NIR image were acquired and transferred to the main system where the image processing takes place. Since this method can't be done due to need to go to the greenhouse farm for a test of actual lettuce, we have conducted an alternative method which was almost the same as the previous one. Instead of capturing an image, the user can now upload raw images to the system, and this gathered image will be processed for analysis. Two same images will be uploaded from the user to the system, wherein the first image serves as the RGB and the second image was modified to see the image in terms of NIR reflectivity. With this, the reflectance needed for computation of the three vegetation indices can be obtained. However, the image still needs to undergo segmentation in order to separate the foreground or the main target, which is the lettuce, to the background noise. After the image segmentation had took process, the vegetation indices can now be calculated. These indices were used as a standard index in assessing the lettuce parameters in terms of health, water stress, and chlorophyll content. The NDVI was the main index used in the study. Through NDVI, the said parameters can now be identified based on the calculated intensity in terms of NIR and the red region. As said earlier, high NIR intensity leads to an increase in NDVI, indicating the plant is healthier. The two indices were used as a supporting indices only for the NDVI.
The user interface created the sign up feature to create user accounts so that each data will be kept in a secured account for confidentiality. Upon logging in, the user will be prompted to the About Us page, which shows a bit information about the study. The Dashboard tab is where the images were inputted and processed. That is where present and previous data are logged. Yoki's farm in Cavite agreed to be a part of the data gathering of the study. Unfortunately, due to the sudden circumstances, both parties decided not to push through the procedure. To compensate this, available images of green leafy lettuces were downloaded and served as input to the system.
In terms of obtaining results for the aerial vehicle, we evaluated the system based on its flight stability, since clear images can only be obtained if the aerial vehicle would hold at a given altitude with good stability. The best way achieving this was by reducing vibrations experienced by the vehicle itself. This parameter can be analyzed and viewed within the aerial vehicle's ground control station. At the initial testing, the measured vibrations are extremely high, causing the drone to easily crash at some times of flight operation. The best ways to reduce this vibration is by cutting the weight, by using vibration pads, and changing the waypoint navigation parameters. The weight of the drone was actually reduced by 400 grams by exchanging some of its hardware, especially the LiPo battery. As we all know, the heavier the system, the more the motor struggle in lifting the UAV, causing more vibrations to occur. Similarly, mounting the flight controller with a vibration pad for these pads compensate the vibrations experienced by the frame of the UAV. Lastly, waypoint navigation parameters states the speed and acceleration of the UAV at autonomous navigation. Putting the UAV at a very low or very high movement causes too much pressure to the frame of the aerial vehicle, especially if there is wind resistance. We vary these values by physically assessing how the UAV would behave at certain speeds. The most important parameters are vertical parameters. We have highly observed that low maintaining speed or acceleration makes the aerial vehicle struggle in lifting itself. On the other hand, increasing too much its maintaining speed or acceleration drastically moves the aerial vehicle vertically too quickly, and if we observe its landing, a high maintaining speed and acceleration makes the aerial vehicle not land properly on its feet due to its speed.
In this section, the processed image and computations done will be analyzed on how the system identifies the health, water stress, and chlorophyll content of the lettuce. The specific colors of RGB were obtained by color family or pattern of the image because the vegetation indices were mainly based on color mapping. Bagwis had its own created color pattern where this can be correlated to the pattern provided by NDVI software and from the thermal imaging spectrum. Observing the processed image from the first figure of lettuce, abundancy of the green color can be observed. This abundancy can generate a maximum intensity level of positive 1, meaning that the cellular structure of the leaves can reflect more near-infrared light than visible light. On the other hand, lowered values of color, referring to the created NDVI spectrum, indicates decrease of the plant's health and dryness since NIR light was highly absorbed rather than reflecting it. This means that from the first figure, the plant was considered healthy and high in chlorophyll content as high value of NDVI was calculated or more NIR intensity was reflected. From the second processed image, shades of blue and red results to a decrease in the NDVI since the visible region was more reflected than NIR intensity. Another used indices were the PRI and CVI. As mentioned earlier, these are only supporting factors for the NDVI. The NDVI itself can already assess the lettuce's parameters such as health, water stress, and chlorophyll content. The PRI is sensitive to changes in the yellow-red pigments of the plant, meaning the ideal value would be high if the intensity level is greater in the visible region rather than in the NIR. If the computed value of PRI was high, the lettuce is more likely to be stressed. However, the system may sometimes give a different value because the system more relies mainly on the standard spectrum of NDVI. The same goes for CVI, which can detect chlorophyll content. The Bagwis spectrum was compared to other two spectrums, the NDVI color mapping software for health indication and thermal imaging for water stress assessment. The color mapping of Bagwis was correlated to the NDVI software where green indicates high chlorophyll content depicting the plant is healthy. The thermal imaging spectrum was mainly based on temperature. As the temperature increases, transpiration or flow of water decreases. The decrease of water movement means that the plant is stressed. Therefore, from the spectrum, red depicts high stress level wherein this region in the Bagwis spectrum results to a nearly zero value.
It is necessary to consider the drone's weight, speed of its flight, and materials used to properly calibrate the drone's stability during flight. For the drone used in this paper, a mass of 1.2 kilograms was able to do a continuous flight of approximately 10 minutes with an acceptable stability. For the camera system, although parameters were identified, in concluding the health of the crop, it was found out that combining PRI and CVI gives contradicting values to each other, and therefore majority of decisions were analyzed from the value of NDVI.